Welcome everybody to lecture 2 for Chemistry 1001. We're going to be talking about some quantum mechanics today. And the first thing I want to look at is the wave nature of matter. And we saw that Louis de Broglie determined that electrons possess wave behavior. It had been known for a long time that they possessed particle behavior, and that was easy to show. To see that matter possesses wave behavior was something of an anomaly from what they had originally anticipated. So we know it's a particle with mass. Now it's a particle that behaves as a wave as well. And the way that they showed that is to show interference patterns by taking a beam of electrons, passing them through a double slit, and rather than just getting two spaces of just electron hits, instead what they ended up with is interference patterns like we see in waves. So that showed that electron beams actually possess wave characteristics. And if you've ever seen the type of interference pattern, what you see is areas of reinforcement and areas of cancellation, reinforcement and cancellation, just alternating. And what that means is that electrons actually interfere with themselves as they travel through space, which is really kind of a strange concept, but it was hard to deny the data that the experiment showed. Now, where this eventually gets us to is this idea of the Broglie wavelength, which we're not going to explore here. It does get us to the uncertainty principle, as well as this idea of indeterminacy. And we really want to focus on this idea of indeterminacy because it really sets up how we view electrons around an atom. So for indeterminacy, we're really looking at a deterministic versus a non-deterministic point of view as far as where objects are and where they're headed. And this is where we really started to get a split between classical mechanics, which you may have studied in school looking at Newton's laws, versus quantum mechanics, where you're really looking at things down at the atomic level. And if you have traditional classical physics, if you calculated the trajectory of something, you knew its original speed and you could find its path at any point during its flight. Whereas if you had something like a probability, all you could say is, well, we think that we're going to find it in this region. And that was about as good as you could do once you got down to the electron level, the atomic level. And so what this eventually gets us to is that electrons that are in atoms, as they're moving around the atoms at about a tenth of the speed of light, they have very well-defined energies, and we can calculate those energies fairly easily. But the problem is we cannot calculate their positions or their paths very easily. And actually there's a what's called an uncertainty principle that says the better we calculate the position, the less we know the trajectory, and vice versa. And so a given energy has several different positions, and because of that, we also don't know the path particularly well. Now, if we take a look at a graph of what a cannonball might look like in the classical trajectory, if a cannonball were fired at a particular angle with a certain feet per second or meter per second velocity, it would be expected to follow a certain path, and we could calculate any point on that path. However, over here with our quantum mechanical distribution, what we see is we get just a distribution of expected positions, and it becomes impossible to determine where something actually is. We can actually see that there seems to be a little bit higher density right there in the center, close to the classical trajectory, but again, it's no guarantee that that's where something's going to be. And here we have a baseball game where a pitcher is trying to always throw the ball into the catcher's mitt. And we can see for the most part, most of the balls do go in there, but we see that you get it scattering out here as well. Okay, so we think we know where it's going to go, but in fact we really don't. And that's very similar to how we treat the electron. Now, Schrödinger equation is a very important equation in quantum mechanics. It It's not particularly useful because it's actually a very complex equation once it gets all broken down into its bits and pieces. But initially, it looks like a fairly simple equation. And given what it's trying to describe, it actually can be kind of coalesced quite easily into this equation. H psi is equal to E psi, where H is actually an operator, and that's where a lot of the complexity comes in because it is an operator. The psi symbol here is actually the wave function, and the wave function is a combination of a sine function as well as an exponential function multiplied by each other. And there's a couple other small components in there as well, a couple of constants. But those are generally what give that wave function their shape. And then the E here is the actual energy. And when those operator times a wave, their operation on a wave is equal to the energy times the wave function, then you've solved the Schrodinger equation. Unfortunately, you can only solve it for a single electron atom, and that, of course, is only hydrogen. So we just don't have the mathematics capable of solving the Schrodinger equation for anything more complex than hydrogen. So we mentioned how psi describes the wave behavior of the electron. Something else you'll see here in some graphs is this idea of probability density, very similar to what we saw in that trajectory graph on the previous slide, and that would represent psi squared. So solutions to the equation, I mentioned that the Schrodinger equation can only be solved for a hydrogen atom. And when we do solve that, we get what's called an orbital, which is a graphical representation of that wave function, and allows us to see where in space we can expect to find that electron. So each orbital that we solve for has 3 related quantum numbers that help us define the wave function. It has 3 components that get worked into it. We have the principal quantum number, which we call n. We have the angular momentum quantum number, which we call L. We have the magnetic quantum number, which is called m sub L. And so those 3 quantum numbers help define the wave function and where it is in space. We're going to go through each of those in a little bit more detail. And we have one last quantum number that doesn't go into the Schrodinger equation, but it does play a major factor in looking at electron configurations and helps us see how electrons are arranged around the nucleus of an atom. And that's the m sub s, the spin quantum number. So the principal quantum number n, it's called that because it is the most important quantum number there. It determines both the size and the energy of an orbital. Possible values are any integer greater than 0. So n can equal 1, 2, 3, 4, 5, 6, all the way up to whatever number we can go up to. Typically, we see 1 through roughly 6 or 7 is about as high as we really witness. Now, the energy of an electron that's in an orbital can be calculated using this equation here with a constant, Rydberg constant, and we just take 1 over n squared, where n is the n value, the principal quantum number there, and then we just multiply that by the Rydberg constant. And when we plot that out, what we get is a plot of energies, and we can see that the energies get closer and closer together as we go up in n value. Okay, it's not that the orbitals are getting closer physically, they're just getting closer in energy. Angular momentum L determines the shape of the orbital. We have lots of different shapes of the orbitals. The values allowed for L are a little bit more complex than n. So they're numbers that start at 0, and they can go all the way up to n minus 1. So the value of n helps determine what the value of L can be. Okay, at least it determines the limits. So L can be equal to 0, 1, 2, 3, etc., up to n minus 1. So if we have an n equals 1 orbital, or we're in the n equals 1 shell there, the only value I can have for L is 0. I can't have an L equal to 1 because I can only go up to n minus 1. If we go up to the next highest n level, 2, then I can have 2 different L values. I can have an L value of 0, or it can have an L value of 1. And the number of possible L values will always be equal to n. So we saw that if n is equal to 1, we have one possible L value. With n equals 2, I have two possible L values, and that just keeps going all the way up. That's always true. And a lot of times what we do, rather than use the numerical value of L, is we give a letter value for an L value, and we can see what that looks like here. So if we have an L value of 0, we give that a letter designator of S, and we can also think of that as an S orbital. Okay, and for P, that's if L is equal to 1, so you can think of that as a P orbital. And I can write that all the way down. If L is equal to 2, we have a D orbital. And if L is equal to 3, we have an F orbital. Okay, so that's all L does, is it really helps us define what type of orbital we have. Now we also have our magnetic quantum number. So we had N that determined the size, we had L that determined the shape, and M sub L determines the orientation of that orbital in space. Which way is it pointing? And M sub L has also allowable values, and they are dependent on the value of L. So M sub L can go all the way from minus L up to plus L, including 0, so all integer values between there. So if we had an L equal to 1, a p orbital, M sub L could be equal to minus 1, 0, or plus 1. And if we had an L value of 2, we can go all the way from minus 2 up to plus 2. And then we get our last quantum number here, our spin quantum number, M sub s. It specifies the magnetic spin of an electron in an orbital. We only have two possible values for magnetic spin. It's plus 1/2 and minus 1/2. We just refer to these as spin up and spin down. And because there's only two allowed values, this becomes really important when we start occupying the orbitals with electrons, because what that means is that each individual orbital can only hold two electrons, one that's spin up and one that's spin down. And we'll see why that is in just a little bit. So we mentioned earlier that our L values are usually named as letters, so S, P, Ds, and Fs. And when we're referring to orbitals, we reference them primarily by just the N and the L values. So the L value, again, is given a letter designation. The number of sublevels that we have is always going to be equal to N. And the total number of orbitals within an N level is equal to N squared. If we look at the number of orbitals in a sublevel, so a sublevel would be an L value. A sublevel will be equal to 2 times L plus 1. And this all brings us to orbital shapes. Okay, so orbital shapes, when we're looking at where bonds form between atoms, the shapes of the orbitals become very important because bonds are formed by the overlap of atomic orbitals. So orbitals tend to have certain shapes, as we saw, and or as we just talked about. And so those areas of electron probability have to overlap, and that tells us that nuclei are sharing those electrons by overlapping those orbitals, and that's how we get an atomic or a bond between two atoms. And so the shapes of those overlapping orbitals and where they lie around the atom help us determine the shape of the molecules. So s orbitals have a very specific shape. They are spherical. We generally represent their size at a 90% probability of finding the electron within that volume. And we have to go to a 90% probability to bring that s orbital down to the atomic level. As we raise that probability higher, we make that orbital larger and larger and larger until it's not very usable anymore. So we have this idea of radial probability, and we can see that we have a maximum probability of finding the electron around 52.9 picometers away from the nucleus. However, you can go all the way out, and as this distance goes farther away from the nucleus, the probability drops and drops and drops, but it never actually reaches zero, which is why you have to basically have like a 90% integral kind of here. At what point do I have 90% of the area underneath that curve? In that distance is where we would draw the edge of our s orbital. It's not important what the value actually is. We mentioned that. I mentioned that. Okay, if we go away from the 1s orbital and go into the 2s and 3s orbitals, so remember 1s is for the n equals 1 shell. That has an s orbital. The 2s, or the n equals 2 level, also has an s orbital, and the n equals 3 level has an s orbital as well. So all of those orbitals are in fact spherical, but as you move away from the n equals 1, you start to get to nodes, and nodes are regions of zero probability density. Very similar to if we have a rope that you're flipping up and down. Once you get a standing wave, you get areas of zero displacement of the rope. That rope doesn't actually move up and down, it just kind of moves back and forth. And so it has a zero wave displacement. And we get that same type of behavior in our orbitals because they do involve sine waves. Remember, your sine waves do cross through a 0 point going from positive to negative. And so here's what we end up with on our graph here. So you can see in the little white, when we look at this little core area here, there's an area of high density right near the nucleus, and then we actually go through an area of zero probability. So right at that point, there is zero chance of finding an electron, which is kind of interesting because you got to ask yourself, how does an electron get from being in the center to being out here without passing through an area of zero probability? So it's just kind of an interesting thought. As we get bigger to the 3s, what we see is we have an additional node, and for every n level that we go out, we'll actually gain another node. And so you start spreading out that distribution of electron probability. If we look at our p orbitals, they start with n equals 2, so there's no such thing as a 1p. They start with a 2p and then go up from there, so you have 2p, 3p, 4p, etc. They are symmetric within a plane. They have two lobes of electron density, and we get a node right at the origin. And we'll take a look at what one looks like here in just a moment. Because of the m sub l values, we get 3 p orbitals per level, and these correspond to the m sub l values of -1, 0, and +1. And remember that m sub l is what determines the orientation in space, or the direction that they're pointed in space. And we can think of these different m sub l values as pointing along the x-axis, y-axis, and z-axis. And so we actually call those p orbitals the px, the py, and the pz. Now for our d orbitals, we have the d orbitals L equals 2. Actually, let me go back because I thought I had a picture of the p orbitals there. And we'll just get right back to this point. There we go. And so our p orbitals are actually going to look something like this. So we're going to have a lobe there, then we'd have a lobe there, and we might get like a minus lobe and a plus lobe, and we see that they're symmetric across that axis there. And this is where our node is as well, right there in the center. So there's a zero probability of electron density right between those two lobes. Now let's take a look at our d orbitals, and these are our L equals 2. They start with the n value of 3, so there's no such thing as a 1d or a 2d. We just start at a 3d, and then 4d, 5d, 6d, etc. Each level has 5 d orbitals corresponding to our m sub Bell values of -2, -1, 0, +1, and +2. 4 of the orbitals have a very easily recognizable cloverleaf shape with 4 lobes and 2 nodes. And then we've got one other orbital that has a slightly different appearance. It looks like a p orbital with a donut around it. We've got some different notations here for the orbitals. We have the dxy, the dxz, and the dyz, and those indicate the planes that they're in. So the dxy looks like a cloverleaf in the xy plane. The xz looks like a cloverleaf in the xz plane, etc. The dx squared minus y squared here actually lies along the x and y axes. So it lies right along with the dxy orbital, but it's shifted by 45 degrees. We can take a look to see how that appears. And so here we have we got the dyz in the yz axis here, like that. We've got the dxy, and so those lobes are actually in between the axes. We've got the dx squared minus y squared, and those lobes are going to fall directly on the xy axes. And then here we see this dz squared where we've got what looks like a p orbital there, and then it's surrounded by a donut. And there's actually a node in between the donut and that p orbital there. And so this brings us to electron spin. And they first found it by zipping a beam of hydrogen atoms through a magnetic field. We know hydrogen atoms have just a single electron. And so what we saw is the beam split into 2 parts. And it was discovered that the reason it did that is because there are 2 different possible spins on those electrons, and so the atom has a certain magnetic spin as well with just that one electron. Now that really only works with a hydrogen atom because it only has the single electron. Now where does that magnetic field come from? Well, it comes from the electron because it's a charged particle and it is spinning, which gives it a magnetic field dependent on the direction of the spin. We can have a spin up or a spin down, and here we see that we have a beam of electrons going through. There's a very tiny focusing hole here, and so that produces just a single beam. And then once they pass through the magnet with north and south poles, some are attracted to the north, some are attracted to the south, some are repelled by the north and repelled by the south, and they went in their respective directions depending on whether they were attracted or repulsed. And so magnetic spin helps us use something called spin notation, which, as I mentioned earlier, helps us arrange our electrons into orbitals using electron configurations, or another thing called orbital diagrams. So in an orbital diagram, each subshell is labeled and each orbital is noted by a square or a line. Now if we write out an electron configuration right here, okay, what we see is we write out our n level 1, our L level S, and the number of electrons present in that orbital. Now, hydrogen just has the single electron, so that one electron is just going to go into the 1s orbital. Now, if I wanted to write an orbital diagram, I can write it with that box. I also could have just written it with a line and that single electron there and just label that line as 1s. Now there's some rules as to how electrons will fill up their orbitals, and the Pauli exclusion principle is one of the most more useful tools that we have for that. That states that no 2 electrons in an atom can share the same set of 4 quantum numbers. It's a lot like an address. It's just like there's no house within a country that can have the exact same address. And so because of spin limitation, that means that each orbital can only hold 2 electrons, because each orbital has, a single orbital has the same n, L, and m sub L values, and then with the m sub L values, there's only 2 possible values, and so we can only put 2 electrons into each orbital. Let's take a look at an example here. So for helium, helium has 2 total electrons, and so we write that as 1s2, like we did right here. And so our orbital diagram looks like this, or we could have just done it with a line, and that's our spin up and spin down with the half-headed arrows there. Now, if we want to see what our quantum numbers are, we see that they both have an n of 1, like that. They both have an L of 0 because both of those electrons are in an s orbital. We have an m sub L for both of those as 0 because that's the only allowable m sub L value for s orbitals. And so now we've got an m sub s of plus 1/2, so that's this orbital right here. And then we've got an m sub s of minus 1/2, and that would be that orbital, or that electron right there. And at that point, I've exhausted all of my possibilities for the 4 quantum numbers in that orbital. So we've said that those electrons from the hydrogen and the helium go into that 1s first. And one of the things that tells us how those electrons are going to fill is Hund's rule. Okay, and Hund's rule states that when you're filling orbitals that have the same energy, electrons will go in as singles, and then, or they'll go in as singles with parallel spins before they start to pair up. And the reason for this is that there's a repulsive interaction between electrons within the same orbitals, and that raises the energy a little bit. Okay, so let's see how this works. If we have a carbon atom, they have electron configurations of 1s2, 2s2, 2p2, and we see in our 2p, we could have written our 3 orbital levels here, and a lot of people would have wanted to do that. I have 2 electrons in the 2p, so why don't we just pair them up right there? Well, that doesn't work because it's easier and takes less energy to put the electrons in like this in 2 different orbitals with a parallel spin. That's the lowest possible orbital. Here, or energy, here we have 2 electrons that are in the same orbital, so that they have to overcome a repulsive interaction because the electrons are both negatively charged, and that raises the energy, and so that's not the lowest possible energy configuration. Now, we're not going to go too much into the concepts of penetration and shielding, but because of those 2 factors, it's why orbitals don't fill completely in n-level order. Because of penetration and shielding, we start to have outer sublevels go up in energy, so they get raised, and your inner sublevels begin to go down in energy, and so their energies come down. And what that leads to is an overlap sometimes between the n levels, adjacent n levels. And it starts with the n equals 3 and n equals 4 levels. And let's see kind of how that goes here. So here's our ordering of orbitals. So electrons start in the 1s, they go to the 2s, 2p, 3s, 3p. That all goes just like we would expect. However, here they begin to go into the 4s before they start going into the 3d. We see that the 4s is slightly lower in energy than that 3d. Okay, and the reason for that is the 3d orbitals here are shielded from the nucleus, so they don't feel an attraction towards that nucleus, and that raises them in energy from the 3p's. The 4s's, on the other hand, electrons in there are very close to the nucleus, so they feel an attraction, and so their energy gets lowered down from what you would expect. And so the 4s goes down in energy, the 3d goes up, and it leads to an overlap of those orbitals as far as their filling order, And so we don't always see the filling order we expect. And we see several goofy interchanges and overlap between the orbitals as we go up. So we go 4s to 3d to 4p to 5s to 4d, and then it just kind of keeps going. Now, when we're writing out an electron configuration, basically saying where are all the electrons, we can use the periodic table to tell us where all these electrons are going to go. And when we're writing out the electrons, we have a couple different ways of doing it. So for aluminum, which has 13 electrons, the first two go into the 1s, the next two go into the 2s, the next 6 go into the 2p. There's 3 orbitals in the 2p, and each of those orbitals can hold 2, so that's how we get 6. The 3s can hold 2. Now I only have 1 electron left, so that becomes a 3p1. Now we see that the first part of all that, ns1 or 1s1, 2s2, 2p6, is the exact same as the electron configuration for the noble gas neon. And so we see that those match there. And so what that allows us to do is to take this part of the electron configuration and just say it's the same as neon with these things added on, 3s2, 3p1. So that's what's called noble gas notation. It's not as big a deal for smaller atoms like aluminum, but when you start getting into big ones like lead and gold and some of those really large transition elements, it's really nice to use noble gas notation because you don't have to write out quite so many things. Okay, it also helps us determine the valence electrons for an atom. A lot of times you have only valence electrons written in the noble gas notation. When this doesn't happen is when you're dealing with transition metals, because you also would have to have some d electrons in there, and those are never valence electrons. Let's talk about this term, valence electrons. So as we move across a period, filling in electrons, they always go into the same n level, at least until we get down to n equals 4. Okay, and then when we move to a new period, so we go down one row in the periodic table, we then move to the next highest n level. Now the number of electrons that are in the highest n level are what we call valence electrons, and this is a very important term here, the highest n level. So the electrons in your electron configuration that have the highest n level. The reason we're worried about those is because at the highest n level, they're the highest energy, means they're the most unstable, and they're the most likely to either be exchanged or to accept electrons from other atoms for bonding. Let's look at an example of germanium here. So let's look at the electron configuration for germanium. It has an atomic number of 32, which means it also has 32 electrons. So we're going to have our 1s2, 2s2, 2p6, 3s2, 3p6, that brings me up to 18 electrons, 4s2, 3d10, and then 4p2. Okay, so there's my electron configuration. If we look at our valence electrons, we look at that highest n level, and we see the highest n level is 4, and so only those electrons that have an n level of 4 are considered valence. We do not consider the 3d10 to be valence. They are still core electrons because they're in the n level that's below 4. Even though they were higher in energy initially, once those 3d orbitals start to fill in, they stabilize, and they stabilize below the level of the 4s. So the periodic table becomes a tool for writing electron configurations, and there's lots of different ways that I know people have learned for writing electron configurations. Sometimes I like to use the periodic table because it just gives us one more something that we always have access to, and not something that we have to remember when dealing with chemistry. I don't have to remember how all my values are arranged or how my diagonals are arranged or something like that. So at the periodic table, you can always find that last electron to fill in by finding where the element that you're looking at, where it lies on the periodic table. So we have different blocks in the periodic table. We have S blocks, and those fill in as NS, where N is the period. So as I'm in period 2, I'm filling in the 2S. If I'm in period 5, I'm filling in the 5S. In the P block, it's also fill in as NP. So as I'm in the period 4, I'm filling in the 4P. If I'm in period 2, I'm filling in the 2P, etc. For the D block, those fill in as the period minus 1D. So if I'm in period 4 and I'm in the D block, I'm filling in the 3D. If I'm in period 5 and I'm in the D block, I'm filling in the 4D. And we see something similar with the F block, except it's N minus 2. So if I'm in period 5, actually that doesn't work, I'd have to be in period 6, and then I would be filling in the 4 Fs when I get into my F block. Now, where do these blocks lie on the periodic table? Okay, well, we have an S block here, our first 2 columns. The D block are where the transition metals are. The P block are the 6 rightmost columns in the periodic table, and then we get the F blocks down here below everything. But if we look at something like chlorine, we can track chlorine's electron configuration as we go across the periodic table. Whoops, didn't mean to do that. There we go. So let's go ahead and do chlorine's electron configuration. So we know chlorine is going to end in 3p5 because it's a p block element, because it's in the p block. It's in n equals 3, and it's the 5th element over. So that's where I get that 3p5. So we can fill in everything. We're going to go 1s2, 2s2. I just keep doing this until I get to my element. 2p6, 3s2, 3p5. And so that's how I get my electron configuration for chlorine. Let's try another one. Okay, how about selenium? We've got to go through a little bit more here. And so I'll change over to red just for fun. We go through the first 2. That's my 1s2. I go through the 2s block, 2s2. I have to go all the way through the 2p block, so 2p6. I have to go all the way through the 3s block, 3s2, all the way through the 3p block, 3p6, and now I'm down to the 4s, so 4s2, and now I'm in the D block, and so that becomes 3d10, okay, and then I finish in the 4p, and I have to go 4 over, so 4p4. Okay, so that's how we can use the periodic table to tell us exactly what the electron configuration is going to be for a given element. Now, some of you may see electron configurations, or you may have seen them in the past, where your 4s2 for this might be written here after the 3d10, and that's fine. It still means the exact same thing regardless of whether you write the 4s2 before the 3d or after the 3d, doesn't matter. Now, one of the things we can use our electron or orbital diagrams rather for is to determine if an ion or an atom will be attracted to an external magnetic field or not. And if it is attracted to an external magnetic field, we call that paramagnetic. Okay, we can look at something like a silver atom here, Ag, just Ag, has an electron configuration of krypton, 5s1, 4d10. You see we've got that noble gas notation working right there. We see in our orbital diagram that we've got just the one electron there in the 5s, and we've got 10 electrons in the 4D, and we see that we've got an unpaired electron. So in order for something to be, I thought I had this in here, in order for something to be paramagnetic, it must have an unpaired electron, just like we've got here. So paramagnetic means you have unpaired electrons. For diamagnetic, it means that all of our electrons are paired, and it means that that atom or ion has no attraction at all for an external magnetic field. Let's compare a zinc atom to a zinc ion. A zinc atom has an electron configuration of argon, 4s2, 4d10. We see that every single one of our electrons in there is paired. If we do a zinc ion has a 2+ charge, and we see that it is also diamagnetic. Now that tells us a couple of things. Notice that the 2 electrons came out of the 4s because 4s is valence and the 3ds are not. When we form an ion, we start by removing valence electrons first. And so if we didn't do that, that means we would have actually removed 3d electrons first, and we would have seen a paramagnetic ion with a diamagnetic atom. But we don't see that. Instead, what we see is both ion and atom are diamagnetic, and so we know that the 2 electrons must have been taken from the 4s and not from the 3d. So this brings us to a little bit of a different concept here. We're getting away from the little quantum mechanics part. We're going to shift a little bit more towards structure and bonding and see how bonding actually occurs. So ions and atoms can be represented by using just dots as electrons as we go around an atomic structure. Valence electrons only is what we use, and so we add them as single dots for the first 4, kind of in the 12, 3, 6, and 9 o'clock positions. And then if we have more electrons to add in, then we can start to double them up. So if we have something like oxygen here, this would be our dot structure here. We can see how we would construct that. So let's just put an oxygen atom right there. And now I'm going to fill in my dots. I know I've got 6 valence electrons from my electron configuration. I also know it has 6 because it's in group 6 in the periodic table. So 6 valence electrons, I'm going to fill in by putting 1, 2, 3, 4. And now I still have 2 more to put in, and so I double these up here. And so from a dot structure standpoint, I have 2 lone pairs of electrons and 2 singles. Let's look at some other examples here. Sodium, if we look in the periodic table, we see sodium has 1 valence electron. So I could put a dot right there. It doesn't really matter where I put the dot. We can look at fluorine. Fluorine has 7 valence electrons. So we're going to go 1, 2, 3, 4, 5, 6, 7. And there we see we've got 3 pairs of electrons and 1 unpaired. We can look at phosphorus. Phosphorus is in group 5. So I got 1, 2, 3, 4, and 5. So phosphorus has 1 pair and 3 unpaired. And then neon is noble gas, and it has 8 electrons. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8. And so we see that neon has 8 electrons around it. It's kind of where we get this idea of an octet of electrons being stable. All of our noble gases, with the exception of helium, have 8 valence electrons around them. So how do we use these Lewis structures? Well, we use it to try to predict how atoms will bond in a compound. Mainly, how are they connected, and how can we put our atoms together in order to fill every atom's octet around them. We want that octet because those atoms want to look like the noble gases, because that will make them the most stable. Since noble gases are the most stable, we figure that if we can get atoms to look like noble gases, then they will also be stable. So in that previous slide, we saw neon having 8 valence electrons, And so we use that idea to try to figure out how many electrons an atom will either need to gain or to lose to look like a noble gas. Okay, here's an example of magnesium and fluorine. We see the magnesium here has 2 valence electrons. Okay, they're just kind of sitting there smiling at you a little bit. We see our fluorine has 7 valence electrons here. It's kind of missing a spot right there. So we know the chemical formula for magnesium fluoride is MgF2, and we might wonder, well, why is it F2? Why isn't it just MgF or MgF3 or Mg2F5 or some other combination of magnesium and fluorine? Well, it has to do with the number of electrons that can be exchanged. Okay, if we look at magnesium, if it can lose, well, we can look at 2 options here. To get 8 electrons in its valence shell, it can either gain 6 electrons or it can lose 2 electrons. Okay, whichever number is less, that's going to take the least amount of energy, and that's what that atom is going to do. So magnesium is not going to gain 6 electrons to look like a noble gas. It's going to lose 2 electrons to look like a noble gas. So it wants to lose those 2. So fluorine, on the other hand, can either lose 7 electrons or it can gain 1 electron to look like a noble gas. Well, again, we're not going to lose 7 electrons. It takes way too much energy, and so it just wants to gain that 1 electron. So each fluorine wants to gain 1 electron. So this magnesium says, hey, you know what, fluorine, I can give you 1 here. Do you want the other one? And fluorine says, no, I don't want another electron because I'm good after I get that 1. But I've got a friend who needs another one as well. So that one goes to another fluorine atom. And now we've got a magnesium 2+ ion because it lost 2 different electrons. And we've got 2 fluorine ions, each having gained 1 electron. And so now we've still balanced all our charges. We've still accounted for all of our electrons. And both magnesium and fluorine now have 8 valence electrons in their outer shell. Now, if we want to look at molecules, so as opposed to ionic compounds, which is what magnesium fluoride is, when you have molecules themselves as opposed to ionic compounds, molecules generally want to share electrons, and the Lewis dot structures are very useful for helping us determine the bonding present there. Once we figure out what the bonding is, we can figure out what a shape might be, so we can predict our shapes. Once we predict our shapes, it helps us predict chemical behavior and some other properties of these different molecules. Now, drawing Lewis dot structures of our molecules is a little bit different than what we did to draw a structure of an atom. So we have a series of steps to go through for molecules. The first thing we need to do is to calculate the total number of valence electrons that we have. So we essentially strip our atoms of those valence electrons, and then we're going to reallocate those electrons in order to create all of our bonds and all of our octets for all of our atoms. So we calculate the total number of valence electrons. We draw the molecule attaching each atom to the central atom with a single bond. Now that central atom is almost always the first non-hydrogen atom listed in the formula. And then we add lone pairs to the outer atoms to complete their octets. Now the thing to remember is that every time you create a bond, every bond counts as 2 electrons. And so you have to keep account of the number of electrons you've used in your bonding, because you can only use as many electrons as you have valence electrons. You can't use more, you can't use less. You can't have parts left over. Okay, once we've added lone pairs to the outer atoms to fill their octets, if we still have electrons remaining, we add those to the central atom as lone pairs. Okay, and if we don't have an octet on the central atom, we may need to bring the lone pairs in from an outer atom or 2 outer atoms to form multiple bonds with that central atom to help it get an octet. Let's look at an example. Well, actually, we looked at examples. These examples are all posted on YouTube, so I'll just go through and show you the different compounds there. One thing I'll tell you to be wary of as you try them on your own is you have to make sure you account for that minus charge on ClF2, because that adds an extra valence electron. Now, when we're doing our structures, there's some properties that we see within our molecules, and we didn't really have a good way to describe why those properties exist. And so a brilliant man named Linus Pauling came up with an idea of electronegativity. It is a man-made value. It does not have a physical measurement. There is no such thing as an electronegativity meter. So we just have these set values that are strictly theoretical. But what electronegativity is, it's an element's ability to pull electrons that are shared in a bond towards itself. The more electronegative an atom is, the more time those electrons will spend around the more electronegative atom. So we have some trends in the periodic table, and a good general trend is as you move up the periodic table from the bottom and to the right, electronegativity increases. So the most electronegative atom is fluorine. We don't count the noble gases since they don't form these types of bonds. So fluorine is the most electronegative atom. Now, when we're expressing a chemical formula, we usually put the least electronegative atom first, and a lot of times that is also the central atom in a structure. Here's our little trend in electronegativity. This is not the best graph. I apologize for it, but this is exactly how it came out of one of my old books. But we can see starting down here at francium with a very low electronegativity. As we go up and to the right, we see a general trend and increase of electronegativity. We do see some little burps along the way here in the transition metals. That's just the transition metals. They're just kind of weird with some things in there. So again, it's a general trend. It's not an absolute trend. The trend, it does hold very well for this area of nonmetals, which is primarily where we use this. Now, due to electronegativity, we get these things called a dipole moment. And a dipole moment is a measurement of the charge separation within a molecule. And this is affected by the polarity of individual bonds, which comes as a result of an electronegativity difference between two atoms present in a bond. So what we get when we have a molecule that has a dipole, and when we say dipole, it just means it has two poles. Something like a battery would be a dipole. It has a plus and a minus. A regular magnet would be a dipole. It has a north and a south. We see in molecules that have differences in electronegativities, we get a partial minus or a delta minus and a partial plus or delta plus. And what we can actually see is these charges will align themselves in an electric field, which tells us that we do in fact have this polarity present. We just mentioned that. We do have a term for molecules that have a dipole. We call them polar. Imagine that. The bonds in these molecules are called polar covalent. So we have a few different types of bonds. We have covalent, we have polar covalent, and we have ionic. So polar covalent means that your electrons are still being shared, so it's still a covalent bond. However, they're polar, which means they're not being shared equally, and we have that separation of charge. Now, once that separation of charge, in other words, that difference in electronegativity, delta En, once it gets bigger than 1.7, then we say that the bond that's formed is ionic. We say that the difference in electronegativity is so large that the electron is essentially spending all of its time around one of the atoms and very little around the other atom. And so that's usually what happens in an ionic bond as well. Now this value of 1.7 does fluctuate from textbook to textbook, so you may see it as high as 2.0, and I've seen it as low as 1.6. That range in there for change in electronegativity is a very gray area. Now, if you have a difference in electronegativity that's small, we say that bond is nonpolar, or we just say it's covalent, which means that the electrons are shared equally. And we usually say that's between 0 and 0.4 for a difference in electronegativity. So here we have 0 to 0.4 for a covalent bond. For its intermediate, notice this textbook had 1.7. The book we are currently using, had 2.0. The book we're using right now has 1.7. For a polar covalent, an example of that would be hydrogen chloride or HCl. Very large would be 1.7 plus is ionic. And the easiest way actually to recognize your difference in electronegativity going to be large for ionic is you're going to have a metal ion combined with a non-metal ion. Those tend to lead to those large differences in electronegativity and leads to your ionic bonds. And here's just a kind of a cartoon showing the different electron sharings. We have our 0 to 0.4, our 0.4 to 1.7. We see those partial minuses and partial positives as the electrons start shifting. It didn't show it very well. Start shifting that way. So the side that has that's more electronegative is going to be the partial minus because the electrons spend more time there. The less electronegative is going to have the electrons pulled away from it, so it gets a partial plus. And then once those differences get too big, we just have an ionic bond with a full minus and a full plus. So we can determine the type of bond for these kind of pairs, and this is the table that you will have on the exam to determine electronegativities. I do not expect you to memorize electronegativities. So if we had a bond between iodine and iodine, well, our delta En would be equal to 2.5 minus 2.5, which is equal to 0. So that would give us a covalent bond. If we have cesium and bromide, cesium is 0.8, our bromide would be 2.8, so we have 2.8 minus 0.8. We always take the bigger number minus the smaller number, and that gives us a 2.0, so that gives us an ionic bond, which we would expect between the metal and the non-metal. And then we have one in here between phosphorus and oxygen. Phosphorus is 2.1, oxygen is 3.5. Minus 2.1, and we get 1.4, and so that would be our polar covalent type bond. So there we've seen all three types of bonds between these different elements. Now this is not something that I'm going to test you on at all, but it's a good thing to know, this percent ionic character. Even though we say that if you have a delta En above 1.7, you're an ionic bond. However, there's really no such thing as a purely ionic bond. There's always some covalent character. There's always a little bit of sharing that's taking place between two atoms or ions in close proximity to each other. And so you can actually calculate the percent ionic character. There's a formula for doing that. We're not going to worry about that. But it does have to do with the measured dipole moment divided by the theoretical dipole moment. So you can actually measure the dipole. Then you have the theoretical one, which is your difference in electronegativity. So just something to be aware of, but again, not something that we test on. It's an important concept, but yeah, no calculations. Now, when we're looking at covalent bonding with our Lewis dot structures, we've always made the assumption that the bonding is localized, which means that the electrons that are shared only between those particular atoms. Every once in a while, what happens, however, is that you have molecules where you get to a point in your dot structure where you have multiple options as to where to put a double bond. Okay, and when that happens, you get something called delocalized bonding, or resonance is another way of saying that. So the actual structure that you get is a hybrid of the various structures, and that delocalization, rather than just choosing one place to put a double bond over another by saying that the double bond can go in both places kind of at once by splitting in half. That's kind of what delocalization is. It lowers the energy of the molecule. And here's an example for ozone. So you get to a point in ozone where you've got this dot structure here. And you have to decide what you want to do for a double bond, because that central oxygen only has 6 electrons. Well, we can put the double bond on the left, or we can put the double bond on the right. But to say that one of those is favored over the other doesn't make any sense. And so instead, we say the double bond is split between the two, and really what you kind of have is a bond and a half there and a bond and a half there. And what that does is it lowers the energy below either of these two structures here. And Mother Nature is always going for the lowest possible energy. So these are examples that I've also posted on YouTube to show how the resonant structures are formed and how you find your different possible structures. Now, earlier on when we were doing dot structures, we did an example on COBr2, and during the dot structure, we assigned the double bond to the oxygen rather than to the bromines. We had enough electrons on the bromines to put a double bond there, but it turns out that the oxygen is better able to handle the double bond. So now we want to ask ourselves the question, why? And the answer lies in a concept that we can use called formal charge. So basically, formal charge is a way of splitting up the electrons around. It's an accounting system, and it determines which atom can best handle a double bond. Or if we have the same type of structures, it determines which one might be favored. So when we're doing formal charge calculations, we need to come up with a dot structure, all the different possible dot structures, and then we need to calculate the formal charge on each atom for each possible structure. Now, thankfully, the calculation for formal charge is very easy. We just split all of the electrons of a bond, and we assign 1 electron from each bond to each of the 2 atoms involved in the bond. If there's any lone pairs on an atom, those belong only to the atom that they sit on. And then we take the number of valence electrons that the atom would normally have, that we find in the periodic table, and we subtract the number of electrons that we've assigned it in the molecule from these upper 2 steps. So those 2 things make up that. Okay, and then the preferred structure has the formal charges on the atoms closest to 0. So again, you've got to calculate the formal charge for each individual atom, and they're usually 0, +1, -1, +2, -2. They don't usually get much higher than that. And so the preferred structure has as many formal charges as close to 0 as possible. Sometimes you run into a case where you have 2 structures that have the same set of formal charges. And if that's the case, then you need to look to see, do you have different elements present in that structure? And if so, the structure with a negative formal charge on the more electronegative atom is going to be preferred. And we can take a look at some examples here in just a moment, this one last bullet. One last thing to make sure you calculate, to make sure that you've done your formal charge assignments correctly, is that the sum of the formal charges have to add up to the overall charge. Now, if it's just a regular uncharged molecule, then all of the formal charges have to add up to 0. if you have a charge on a molecule, so you have an ion, let's say it's a -1 ion, then the sum of your formal charges have to add up to -1. So here's some examples, and again, we did these as a YouTube video, so you can take a look at those. The OCN minus example shows that last rule where you have two structures with the same set of formal charges, but you have to look to see in which one does the negative charge end up on the most electronegative atom. Now, once in a while, we get to molecules where we have lots of electrons, and we end up with more than 8 electrons. When we follow the rules for dot structures, we end up with more than 8 electrons on the central atom. And for some atoms, that's just fine. This idea of an octet around an atom is a good general rule, but we do have some exceptions. Beryllium prefers 4. Boron prefers 6. So these are elements that prefer less than the octet. Once you get to phosphorus, and I should say including phosphorus on here, so nonmetals after phosphorus, can form additional bonds. So they can form more than 4 bonds, or they can have more than 4 pairs of electrons attached to them. And so we call these expanded or extended octets. That's the same thing. So here we see a few examples. Here we have arsenic pentafluoride. We've got the arsenic here, and it has 5 bonds to it. Each of those bonds count as 2 electrons. So the arsenic here has 10 electrons assigned to it. In sulfur hexafluoride, there are 6 bonds assigned to that sulfur, and so that gives us 12 electrons around that sulfur. And that's fine because both of those elements come after phosphorus, and so they can expand their octets. We also see some species with odd numbers of electrons. You will not see that in this class, but just be aware that those type of compounds do exist. Now, one of the last things that we're going to do in this lecture is this idea of VSEPR, valence shell electron pair repulsion. We use this to predict molecular geometry and bond angles. It's based on the idea that pairs of, this shouldn't say pairs of molecules, this should be pairs of electrons will repel in order to get away from each other. So we have electron groups here. So this is a bond that forms between there. And so remember, a bond is nothing more than a pair of electrons between 2 atoms. And so those electrons are all negatively charged, and so they will repel each other and try to get as far away as possible. Okay? When that happens, that leads to the most stable arrangement of those electrons around each other. Now, we're going to work primarily with molecules that just have a single central atom. It can get more complex than that, and I'll show you a couple of examples as we go along that are a little bit more complex. For now, we're just going to work with the one central atom. So some things we need to look at when determining molecular geometry. First thing we need is a proper Lewis dot structure. Okay, we need to count up the number of electron pairs around the central atom. Now, what's an electron pair? It can be a lone pair or a bonding group. Okay, so sometimes we'll say number of electron groups around the central atom. That's probably a better way of saying that. Let me cross out pairs there and put groups. Okay, and again, an electron group is either a lone pair or a bonding group. Okay, where those electron groups form determine where the lone pairs or the bonds will go in the molecule, and these help us determine our shape. So the steps we have to follow: proper Lewis dot structure, determine the number of electron groups around the central atom. Okay, and those are number of bonding groups or lone pairs. Okay, and remember, any type of bond counts as only one group. If it's a single bond, it's one group. If it's a double bond, it's one group. If it's a triple bond, it's one group. Okay, and then we determine the number of bonding groups and the number of lone pairs around the central atom. and then we determine our molecular geometry from a table where we can look up or that you just have memorized. So here's an example of that table. We look at the total number of electron groups here. We look at the number of bonding groups for a particular molecule and the number of lone pairs, and we just go right across. So let's say that we have a structure with 4 electron groups, 3 bonding groups, and 1 lone pair. We have an electron group geometry that's still going to be tetrahedral, so 4 electron groups will always arrange themselves in a tetrahedron. Notice that's the same regardless of the number of bonding groups or lone pairs, because they're all electron groups. Okay, with 3 electron groups, I'm going to have what's called a trigonal pyramid molecular geometry. Okay, and an example of this structure would be something like ammonia, NH3, with that 1 lone pair right there. Notice that for our molecular geometry, we only take into account where the atoms are, not where the lone pair is. We can look at our extended octets here. So we have a whole bunch of different combinations for 5 electron groups and a few different combinations for 6 electron groups as well. So we can kind of go through a quick example. If we do water, we determine the dot structure. That has, we'll just go ahead and put it in here. Okay, actually, let me redo that in a different way, because I drew it as being bent, but we don't know that yet. So there's a dot structure for water. Number of electron groups here is going to be 4. 1, 2, 3, 4. 2 of those groups are bonding. 2 of those groups are lone pairs. So my electron group geometry is going to be tetrahedron, because that's how 4 groups arrange themselves around an atom. And when we look up the molecular geometry with 2 bonding groups and 2 lone pairs, we get something that's called a bent geometry. And the bond angle is around 105 degrees. A pure tetrahedron is 109.5 degrees. However, I have 2 lone pairs, and the lone pairs tend to push the bonding pairs away a little bit, and they squeeze them in about 2 degrees each. So we end up around 105. So there's an example there. If we had a molecule, ClO3, the dot structure is a little more difficult just because we've got that minus sign in there. Our electron groups still have 4. So our electron group arrangement is still tetrahedron or tetrahedral, same as water is. However, different from water, we have 3 bonding pairs and 1 lone pair, and so we get that molecular geometry that's trigonal pyramid. We have that 1 lone pair, so even though we expect angles of 109.5, that 1 lone pair here squeezes that down to about 107. And there's an example with ammonia, NH3, that I couldn't find a picture for ClO3-, but it's the same idea. And here's an example with an extended octet, BrF3. When you do the dot structure, I'm not going to go through all the steps. I'll let you do that on your own, but you get something that looks like this. You have 5 electron groups. 2 of those are bonding, and you have 3 lone pairs around that bromine. Of course, we have the lone pairs out here around the fluorine, but they don't count for the geometry because they're not on the central atom. So for our electron group geometry with 5 electron groups, we have a trigonal bipyramid. 3 bonding groups and 2 lone pairs gives us a T-shaped molecular geometry. And it looks something like that. You can see where the T name comes from. Now, if we go into larger molecules, We're not going to see this very much. I did not go through this in the regular lecture. But sometimes you can have two or even more central atoms. A lot of times we'll just start calling those interior atoms. You see this in organic molecules primarily. And in these cases, you don't have a single molecular geometry. Instead, what you have is a particular geometry around each individual interior atom. So if we look at a molecule here, I forget which one it is, glycine, we see that we've got four interior atoms, the nitrogen, the two carbons, and the oxygen that's still in the chain there. And each one of those has their own set of electron groups, bonding pairs, lone pairs, and we can see that they all have a different molecular geometry around them, just around that particular atom. So there's four different molecular geometries for that molecule. So the molecule itself does not have a geometry. And there it is there. So after finding our molecular geometry, we might ask ourselves, well, what's the dipole of these larger molecules? And how can a molecule with polar bonds be nonpolar, which can certainly happen? Well, if we look at something like carbon dioxide, CO2, what we find with CO2 is two electron pairs. So when we look at the table, two electron groups, both bonding groups, we get a linear molecule. So we have 180 degrees between those two oxygens there. Now, if we look at the polarity of each individual bond, we see that we have a dipole pulling away from the carbon here, a dipole pulling away from the carbon here. However, both of those two oxygens are pulling on all of those electrons. And so what ends up happening is the tug of war between the two oxygens and the carbon just comes to a standstill, and we get a fairly even distribution of electron density around that molecule, and we end up with a non-polar molecule. Even though each individual bond is polar, the two dipoles are acting against each other and cancel each other out. This happens generally when you when you don't have lone pairs and you have a geometry that's completely symmetrical. If you have any lone pairs, you will almost always have a polar molecule. So if you have a geometry that's bent due to lone pairs, it's almost always polar, just like water. And we can see what happens with water is we have a dipole between one hydrogen and the oxygen going up like that. We have the other one going up like that. You use the head-to-tail method of dipole addition, and what we end up with is a resultant dipole going straight up through the molecule. And we get a region of positive charge up here and a region of partial negative charge up here. So that makes water a polar molecule. And a pretty quick and simple table here on how to determine this. As long as all of these atoms out here are the same, you get these type of situations. And so if it's linear, it's going to be nonpolar. If it's trigonal planar, it will be nonpolar. If it's tetrahedral, it will be nonpolar. Again, this is assuming that all of the outer atoms are exactly the same. As soon as you start changing the atoms with different electronegativities, then everything is different, and you've got to start looking at that in a lot more detail, and your problem becomes a lot more complex. So these are all nonpolar, and then you've got a bent structure or a trigonal pyramid structure, both with lone pairs. Those structures have a very real possibility of being polar. All right, that was a lot of slides and a whole lot of material to go through. Hopefully it made sense, and if you have questions on anything that was covered in this particular lecture, make sure you contact me or send me an email or come see me after class.